presentation, I would like to present about switch reluctance and BLDC model. Our group has three members. Firstly, I am Theint Watty, and there are my friends Aung, Paing, and Htet. Uh, Firstly, we are doing this presentation for electrical machine 2 course, and I would like to present what is BLDC model. BLDC motor is a kind of motor operates using different current but without brushes. It uses an electronic controller for commutation, making it more efficient, durable, and quieter. These motors are commonly used in appliances, drones, and power tools. This is the figure of BLDC motor. And in the next slide, I would like to explain how BLDC motor work. First, BLDC motor replaces mechanical brushes with electronic commutation. The motor has permanent magnets and the stator contains winding. Hall sensor detect the rotor's position and the controller switches the stator coils to keep the motor rotating smoothly. The figure A shows the DC motor and the figure B shows BLDC motor. As you can see in the figure, both motors contain contactors, permanent magnet, and rotor to do their functions. In the next slide, I would like to explain what is back EMF and drive system. Back EMF is the voltage generated in the stator as the rotor spins. It opposes the supply voltage and increases with speed. The inverter converts DC into three-phase AC-like signals to energize the stator and rotor control rotation. This figure shows three-phase, and each phase has trapezoidal shape. And in the next slide, it is about six-step commutation, trapezoidal control. BLDC motor use six-step or trapezoidal commutation. Every 60 electrical degrees, two of three phases are energized. This creates a rotating magnetic field allowing continuous rotor motion. Although simple, this method can cause torque ripple. In this figure, you can see the degree difference is 30 degree. The degree difference is 60 degree.
According to Watty presentation, let's take a look at how six-step commutation works. The next slide I'm gonna present is control algorithm and Hall sensor feedback. Actually, Hall sensor don't provide the exact angular position of the rotor. Instead, they detect when the rotor moves from one side to the next. So we need this commutation logic and to determine which winding pair should be energized. It uses the signal from the Hall sensor and it determines. And here for Elizabeth phase, it might be high while phase it might be low. They keep the motor keep rotating continually. The next slide is speed control loop. We use this feedback loop to control the speed, and speed control is done by using the feedback loop. The actual speed here, is compared with the desired speed, and the BIT controller adjusts the body to correct any difference. Higher body lead to faster speed, and lower body cause the slower speed. The next slide is PWM in BLDC model. In real life BLDC motor, the power supply is not fixed and it cannot be directly variable. So we need to use PWM in BLDC motor. It control the speed. The PWM rapidly switch out the body on and off like this, and the duty cycle determine the affected body. The higher duty cycle means the faster speed, and we need to use the higher frequency for smoother performance. BWM control method. There are two BWM control method. The first one is using the back converter, and the BWM control DC level before the inverter, and the second method is without back converter, and the BWM here is directly applying to the inverter switches. Speed and torque control. For this one, we use Paing controller to adjust the BWM duty cycle, and the commutation logic ensure that the correct speed is energizing, and maximum torque is occur when the feed is 90 degrees apart. But in real life, it's very hard to get the 90 degree. So FOC method is used for smoother torque. The FOC method is field-oriented control and is maintained to get a smoother torque. The next slide will show about the simulation result for this circuit. Here, let's take a look at the scope 1. In this scope 1, here, the actual speed got accelerate at fast, and then it got steady state at 450 round per minute, and it deaccelerate and back to 0. The torque waveform show that the torque is constant here when the speed is got steady state, and then it decrease back to 0 when the speed got deaccelerate and slow down. The stator current waveform had trapezoidal shape, and its amplitude is vary according to this torque and this speed. Next, let's see the scope 2. Here in the scope 2, the fast waveform show the trapezoidal flat, and it have the shape like this. And the second waveform is back EMF. It's increased with rotor speed and back to 0 when the motor is slowing down. The Hall sensor is here and is used by commutation logic circuits to determine the switches sequence. The last scope is number 3. And here is the driving cycle speed waveform is accelerate at fast steady state and deaccelerate back to 0. The achieved speed is accurate speed, and it follow the driving cycle speed. That means that this control the speed. And here we can see the little ripple because of the torque and commutation method. Okay, the next slide will be about switch reluctance motor, and it will be explained by Brian.
Let me explain about switch reluctance motor. This is the overviews of switch reluctance motor. So we can see in the screen, switch reluctance motor is an electronic synchronous motor, and it's operate based on magnetic reluctance, and meaning the rotor move to the positions of minimum magnetic resistance. It is simple, robust, and cost effective. So we use in automotive, industrials, and aerospace areas. Actually, its characteristics is like BLDC. So SRMs don't use magnets or rotor winding. So let's move to next slide. This is the structure of SRMs. SRM has a simple construction. So what is this construction? This construction is made of rotor and the stator. The rotor is made of laminated steel with salient pole and a stator with concentrated winding, and torque is produced when the rotor aligns with the energized stator pole. So now I'm presenting 6x4 switch reluctance motor SRM. It means stator with 6 poles and rotor with 4 poles. So next slide. What is the principles of operations? The principles of operations of SRMs is that when a stator winding is energized, magnetic flux is created. That creation of magnetic flux made a rotor to move ally with that flux, minimizing reluctance. By sequentially energizing stator poles, continuous rotation is achieved without magnets. As I told you before, that SIMS do not use magnets like BLDC, so it is the same principle. It is the same principle with that. As you can see here, is a stator rotors with minimum reluctance, and then it is minimum reluctance, and then bed at the left side is maximum reluctance. So now let me present about control methods, SRM control methods. So what are the SRM's control methods? Control methods of SRMs require precise timing. Rotor position is detected using sensor and or estimated with sensorless techniques. Stator windings are switched in sequence to maintain rotation, but control is quite complex because due to nonlinear magnetic characteristics. So what are the applications? Switch reluctance motors are used in electrical vehicle, industrial machinery, pumps, and aerospace actuator application that demands reliability and steady torque. So we can also use in vacuum cleaner like we have to use compressor for that machines, so it is useful for SRMs. So what are the advantages and disadvantages of SRMs? There are many advantages and disadvantages of SRMs, but actually it is quite useful rather than BLDC. So its advantages are it is SRMs are simple and low cost, so can operate at high temperature with high torque. But it's thermally robust with high torque. So but however they have drawbacks such as torque ripple, mechanical noise, and require control system. Let me conclude these presentations. In conclusions, the switch reluctance motor show how simple electromagnetic principle can create powerful motion without magnets or complex rotor designs. Its efficiency, reliability make it a strong candidate for the next generations of electric device. Thank you for listening. My idea is that with continuous advancements in control technology, SRM has a great potential to become more common in future smart systems and electrical transportation. Thank you again.